One thing that really stands out to me about graph theory, they love their definitions. In fact, we're really going to spend this entire first section doing nothing but talking about definitions. So there's going to be a lot of them, and sometimes there's really kind of small, subtle differences between them. So what I like to suggest to people at this point is that they get themselves a set of index cards and write these definitions on index cards, right? You write the term and then the definition on the back. Maybe you put an example, and you keep those in front of you while you're studying and you're working on problems, thinking about things, trying to answer questions. It's a great little organizational tool, and I think you'll find that if you do this, as you use the cards, the more you use them, it'll really help to kind of internalize these definitions. So over time, you eventually kind of wean yourself away and don't need them anymore. So to start with, let's talk about just what exactly we mean by a graph. We saw some examples in the introduction, but let's see if we can make this definition more precise. A graph is made up really of two sets, right? The first one is a non-empty set of vertices. Those are the dots. And a second set, E, made up of what we're going to call the edges. Right, now I want you to notice that non-empty part. Right, a graph has to have at least one vertex, but there is no such requirement on the edges. It's entirely possible for a set to be made up of vertices and no connections at all. All right, and the way these edges are defined, each edge is associated with one or two vertices called its endpoints. There's a number of different ways we can represent a graph. Right, the most common one is kind of the diagrams that we saw some of in the introductory lecture. I've got an example of that over here on the left. This is the graph of the Königsberg situation. And you notice we've got dots representing the vertices, and we've got segments representing the edges, and they're all labeled. Right, different ways we can label them. Sometimes you'll see A, B, C, D. Capital letters are usually used for the vertices, lowercase for the edges. Another common approach, what I've got here, where you just use V's and E's and give them subscripts. Now, another method we will sometimes use is constructing a table. Right, and you see what the table is doing. It tells me it's got a list of the edges, and each edge is associated with a pair of vertices. Those are the endpoints that we're talking about up here. Right, so you see E1 and E2, the table is telling me E1 and E2 both connect vertex 1 to vertex 2, and that is what we're seeing over here in the graph. Right, vertex 1 is up here, 2 is down here, there's E1, and there's E2. Right, both methods have their place. For the most part, we're at least for the first several chapters here, we're primarily going to be sticking to using diagrams. So one important thing I want you to keep in mind as we're talking about these graphs, as we're looking at these diagrams, the situation here is similar to what you saw way back in your high school geometry classes. Remember, in those classes, you didn't really care what the orientation of a shape was. Right, you care about things like side length and angle measures, but this triangle and this triangle, I'm trying to kind of make them congruent, right? So they have the same shape. The fact that one is rotated one way and one is rotated another way, you didn't care, right? And it's the same thing with these graphs. It doesn't matter how the vertices are arranged, how the edges are arranged. When we're drawing the diagrams, we'll often try to do it in such a way that the edges don't cross, only because that kind of makes it clear. But ultimately, the position of things isn't what we're interested in. In graph theory, our sole interest is the connections. Which things are connected to which other things? All right, so if you take these two graphs here, they look quite different, but they are the same. right? Both graphs connect A to B and C. Both graphs connect B to A and C. You've got the same thing over here. You can repeat this all the way around the graph. All the connections are the same. We're actually going to talk some in a later section about exactly what it means for two graphs to have the same shape. Right, so just keep in mind the specifics of how you draw them really isn't something that we're interested in here. So I've got some more definitions here and a graph that we can use to visually see what we're talking about. Right, a loop is an edge with just one vertex. Remember, our definition said an edge is associated with one or two vertices. Right, so if you have a loop, if you have an edge that's only associated with one, that's what we call a loop. Edge E1 over here in the diagram is an example of that. It connects vertex 2 back around to itself. Two or more distinct edges with the same endpoints, or we're going to call parallel. Right? I know we're borrowing an idea from geometry. We're borrowing a geometry term here, right? They kind of look parallel, but don't read too much into that. Again, if you look over here at the diagram, E3 and E2 are what we're going to call parallel because they both connect V2 to V3. They do ultimately kind of touch, right, at those two endpoints. So it's not strictly speaking the same thing as we mean it in geometry. Right, but it is similar in the sense that they're kind of running side by side. All right, two vertices connected by an edge are adjacent, as are two edges that are incident on the same vertex. All right, so what do we mean here? Well, let's look at E4 and E5. These two are adjacent because they share vertex 3. That's what the incident on the same vertex part means. Right? And similarly, let's see, what else can I pick? How about two vertices? Two vertices connected by an edge. So V3 and V4 are adjacent because they are connected to each other by E5. I mean, in the special case of a loop, right, yes, we would say that a vertex is adjacent to itself, right? So V2 up here, that's part of that loop, right? So that would be adjacent to itself. Let's see, a vertex on which no edges are incident is called isolated. That's V1 up here. It's not connected to anything else. It's off by itself, right? No connection to the rest of the graph. And finally, an edge is said to be incident on each of its endpoints. Just a lot of language. You'll get the hang of this, right? Because we're going to be using these terms a lot as we go deeper into the chapter. So we have a variation on a graph here, right? This is what we call a directed graph or a digraph. And it's very similar to a regular graph. It consists of a set of vertices and it consists of a set of edges, right? But in this case, each edge is associated not just with a pair of vertices, but with an ordered pair of vertices that, again, are called its endpoints, right? So you notice how I've diagrammed this here. A connects to E, and the arrow tells me kind of who comes first, all right? So they're capital letters, right? Let me use capitals here. So I would say that AE is an edge in this graph, where I would not say that EA is. Right? And visually, again, these things are often easier to see visually. The arrows tell you kind of who comes first and who comes second. And you see how we described this in the last definition here, right? If the pair VW, V first, W second, is in the edge set, then we say that the edge is from V to W. Right? If you think of a graph as kind of representing a map, right? A digraph or directed graph, this would be a map of one-way streets, right? Kind of a nice little analogy between the two. Okay, a lot to digest there, right? A lot to digest. In the next lecture, we're going to talk about some special kinds of graphs, right? But before you do that, like I said way back at the beginning of this lecture, I really kind of recommend that you find some way to help organize these definitions, all right? So that you already kind of have them there in front of you as you're studying and working. Index cards work great for me. If you've got something else that that you've used before and you're studying and it works well for you, absolutely bring that out and start using that here as well.